In this session, we will be dealing with the chemical vapor deposition method for the synthesis of nanomaterials as well as nanoscale materials like fullerenes, carbon nanotubes and graphenes. So first we'll see chemical vapor deposition method. Here the reactant gases, that is the precursors, they are pumped along with the carrier gas into the reaction chamber, and the reaction chamber it is normally maintained at 700 to 900 degree Celsius. Adsorption of precursors will take place on the heated substrate. Chemical reaction or decomposition of precursors takes place, and one of the products it will get deposited on the substrate surface, leading to the formation of a nanofilm on the substrate. And the byproducts formed during the reaction, they will be expelled out of the reactor. Now, these are the steps involved in chemical vapor deposition method. Now, this shows the diagrammatic representation of chemical vapor deposition method. So here, this method is used for the commercial synthesis of carbon nanotubes. So, for the commercial synthesis of carbon nanotubes, the precursor used is acetylene gas. So, acetylene along with the carrier gas it is normally inert gas which is used to carry the reactant sample. So, acetylene, which is the precursor or the starting material, along with the carrier gas, that is argon or nitrogen, it is allowed to enter into the chamber, and this chamber it is maintained at a temperature of 700 to 900 degree Celsius. And in a quartz boat, there will be the substrate present, and this substrate it will be deposited with metal catalyst like nickel, iron or cobalt. So, when the acetylene gas enters into this chamber at this high temperature, it will decompose forming carbon and hydrogen. So, this carbon nanoparticles, they will get deposited on the substrate, whereby the byproducts formed during the reaction, it is passed out through the outlet of the chamber. So, this CVD method, it has the advantage of high deposition rate and the deposit formed. The nano deposit that is formed on the substrate, it is of high purity. These are the advantages of chemical vapor deposition method. Now, first we'll see nanoscale material, that is fullerene. Fullerene, it is a zero-dimensional allotrope of carbon named after Buckminster Fuller. What do you mean by an allotrope? Allotrope means existence of an element in two or more different forms. That is known as allotropy, and the major allotropes of carbon are diamond and graphite. So fullerene, it is a zero-dimensional allotrope of carbon. Now, fullerenes, they are molecules made up of only carbon atoms, and carbon atoms, they are arranged in the form of a hollow sphere, and it is often compared to a football because of its shape. Therefore, they are sometimes referred to as buckyballs. Here, fullerene, it is also called as Buckminster Fuller because it was named after the architect Richard Buckminster Fuller. Because Fuller's geodesic dome structure, it had resemblance to C60 Fullerene structure. Okay. Now, many number of fullerene molecules with different carbon atoms like C60, C70, C74, etc. have been prepared. But C60 with 60 carbon atoms, it is found to be the smallest, stable and most abundant fullerene. And here the 60 carbon atoms in a fullerene molecule, they are arranged to have 20 hexagonal rings and 12 pentagonal rings forming cage-like structure. This represents the hexagonal rings in the fullerene molecule, and whereas this represent the pentagonal rings in the fullerene molecule. So like this, 20 hexagonal rings are present and pentagonal rings will be 12. 12 pentagonal rings are present, and it has 32 faces. And each carbon atom in the fullerene structure, it is found to be sp2 hybridized. Now, properties of fullerenes. Fullerene, it is a black powdery material, and they are the only allotropes of carbon that can be dissolved in common solvents at room temperature. And it forms a deep magenta solution when dissolved in benzene. It's found to be very tough and thermally stable, and it can be compressed to 30% of its volume without destroying its carbon cage structure. Now, applications. C60 molecule is capable of taking up maximum of 60 hydrogen atoms, and therefore it finds application as hydrogen storage material for fuel cells and some secondary batteries. They are also used in the preparation of superconductors. Then it can be used to carry drug into the cells because the cage-like structure of fullerenes, they can carry drug in them, and they can be also used as lubricants because of the spherical structure. Then they are used in reinforcing structures where lightness and strength is required. For example, in case of tennis racket frames. So these are the major applications of fullerenes. Now we'll pass on to carbon nanotubes. Carbon nanotubes, it is a one-dimensional allotrope of carbon. It's having a cylindrical structure with a central hollow core formed by rolling of graphite sheet. So this structure, it is formed by rolling graphite sheet, so that in the center it will be hollow. Okay, so carbon nanotubes, they exist in two forms, that is single wall carbon nanotubes, abbreviated as SWCNTs, and they are formed by rolling one graphene sheet, and they have diameter in the range 1 to 2 nanometers, whereas multi-wall carbon nanotubes, that is MWCNTs, they are formed by rolling multiple layers of graphene sheets arranged in concentric cylindrical form, and they have diameter in the range 2 to 25 nanometers. And these open ends of the carbon nanotubes, they can be closed with Fullerene caps, because Fullerene, it is having a spherical structure. So when it is cut into two halves, you will get two hemispheres. It can be used for closing the hollow ends or the open ends. Okay, open ends, it can be closed with Fullerene caps. Now properties, CNTs, they have outstanding electrical property, about 6 times than that of copper. And they have highest tensile strength than any other material known. Tensile strength means resistance to break. So they are found to have very high tensile strength. Then carbon nanotubes, they are found to exhibit high thermal conductivity, and they have low density and high mechanical strength. So these are the major properties of carbon nanotubes. Now coming to applications, they are used as electrode materials for lithium ion batteries. Then single wall carbon nanotubes, they are used in solar panels, and carbon nanotubes are used to store hydrogen to be used as fuel source. Now, single wall carbon nanotubes, they can absorb radiation in the near infrared range and can convert that into heat. Therefore, it finds applications in cancer treatments for selectively killing the cancer cells without affecting the nearby healthy tissues. Then CNTs, they can also emit electrons when subjected to high electric field, and that process, it is known as field emission. Therefore, they are used in field emission X-ray tubes. So these are the major applications of carbon nanotubes. Now let us see graphenes. So we saw zero-dimensional allotrope of carbon, that is fullerene, one-dimensional allotrope of carbon, that is carbon nanotube, and graphene, it is a two-dimensional crystalline allotrope of carbon, and it consists of single layer of carbon atoms arranged in hexagonal pattern. And here also each carbon atom, it is bonded to 3 other carbon atoms. This red as well as the green, it shows carbon atoms. So here you can see this red carbon atom, it is bonded to 3 other carbon atoms which are represented in green. Similarly, each green carbon atom, it is represented to 3 other red carbon atoms. So each carbon atom bonded to 3 other carbon atoms in sp2 hybridized state. It is the building block of graphite but has surprising characteristics which makes it called the wonder material. Because computers based on graphene transistors, they have the properties, they have the potential to be 1,000 times faster than silicon based counterparts. And the graphite in graphenes, the graphite layers, they are held together by van der Waals forces. These separate layers, they are held together by van der Waals forces, and layer of graphene stacked on top of each other, they form the graphite. And because of the surprising characteristics it has, it is called a wonder material. Now properties, it is the lightest material known and has high thermal and electrical conductivity. It is the strongest compound discovered. It's found to be 100 to 300 times stronger than steel. And its melting point, it is found to be 4125 Kelvin into a group. It melts into a group of loosely coupled double bonded chains before becoming a gas. And it is found to exhibit unique optical properties. So these are the properties of graphenes. Now let us come to the applications. Graphene, it is a flexible conductor and it is used in solar cells, light emitting diodes, touch panels and smartphones. Graphene supercapacitors, they can be used for energy storage instead of traditional batteries. Advantages include fast charging, long lifespan and environmental friendly production. It can also be used in computer chips, transistors, etc. So these are the major applications of graphene. Thank you.